Why the universe has no size? Let me ask you a question that sounds ridiculous. How big is the universe? You probably have an answer ready. You've heard it before. The observable universe is about 93 billion light years across. That's the number. That's the size. Except it's not. That number is a carefully constructed illusion, a comforting fiction that physicists hand to the public because the real answer is too strange, too disturbing, too destabilizing for most people to accept. The universe has no size. Not in any meaningful sense, not in any way that your brain can process. And by the time I'm done explaining why, you're going to look at the room you're sitting in very differently. I'm Leonard Susskind, and I've spent over 50 years thinking about space, time, and the structure of reality. And I'm telling you right now, the concept of size, the idea that space has a definite extent, that distances are real and fixed and objective, this concept breaks down completely when you push it hard enough. It doesn't just get complicated. It collapses. Let me start with what you think you know. You think the universe has a measurable size because we can see stuff out there. We point our telescopes at the sky, we detect the cosmic microwave background radiation, the afterglow of the Big Bang, and we calculate how far away that radiation originated. We get a number, about 46 billion light years in every direction. So the diameter of the observable universe is about 93 billion light years. There's your size. Except wait. The universe is only 13.8 billion years old. How can something 13.8 billion years old be 93 billion light years across? Nothing travels faster than light. So how did the edge of the observable universe get 46 billion light years away from us in only 13.8 billion years? This is where most people's understanding breaks. And this is where the real story begins. The answer is that space itself has been expanding, not stuff moving through space. Space itself stretching, getting bigger. The galaxies aren't flying apart through a pre-existing space. The space between the galaxies is growing. New space is being created between every point in the universe every moment. And here's the part that will disturb you. This expansion doesn't have a speed limit. The speed of light limits how fast things can move through space. But space itself can expand at any rate it wants. There's no law of physics that says space can't stretch faster than light. And in fact, it does. Right now. Galaxies sufficiently far from us are receding faster than the speed of light because the space between us and them is expanding that fast. You will never see the light from those galaxies. They are causally disconnected from us forever. They exist. They're real, but they are beyond our cosmic horizon, and no signal, no particle, no information from them will ever reach us. Think about what this means. The 93 billion light year number, that's not the size of the universe. That's the size of the part we can see. The part whose light has had time to reach us since the Big Bang. The actual universe, the whole thing, could be vastly larger. It could be 1,000 times larger, 1 billion times larger. It could be infinite. We don't know. And here's the disturbing part. We might never know, because the expansion of space is accelerating. Every year, more and more galaxies cross beyond our cosmic horizon. Light from them will never reach us. The observable universe is not growing in the way you might think. In terms of what we can actually interact with, what we can ever receive signals from, our accessible universe is shrinking. Let me say that again, because I don't think people appreciate how profound this is. The amount of universe available to us is getting smaller, not bigger. Smaller. Every second, galaxies that were once within our reach are being swept beyond the horizon by the accelerating expansion. The lights are going out one by one, and they're never coming back. Now, you might think this is just a limitation of our instruments, a technological problem. Build a better telescope, see farther. But no, this is fundamental. This is built into the structure of space-time itself. No technology, no matter how advanced, can see beyond the cosmic horizon. It's not that the light is too faint. The light literally hasn't had time to reach us, and due to the accelerating expansion, it never will. So when someone says the universe is 93 billion light years across, what they really mean is this is the radius of our ignorance boundary. Beyond that, we're blind. The universe could extend forever in every direction, and we would never know. We're in a bubble, a light cone bubble, and the walls of that bubble are closing in. But let me push this deeper, because the problem with size is much more fundamental than the cosmic horizon. Let me talk about what a distance actually is, because we use this word all the time without understanding how strange it becomes when you apply general relativity to it. In everyday life, distance is simple. You get a ruler, you put it between 2 points, you count how many ruler lengths fit. That's the distance. Easy. Now try doing that across the universe. You can't physically stretch a ruler from here to a distant galaxy. So what do we mean when we say a galaxy is 10 billion light years away? We mean that light from that galaxy has been traveling for a certain amount of time. And given how space has been expanding during that time, we calculate where that galaxy is now at this moment. But here's the problem. At this moment doesn't mean the same thing for different observers. Special relativity taught us that. There is no universal now. Different observers moving at different velocities disagree about what's happening simultaneously at distant locations. So when we say the galaxy is 10 billion light years away right now, we're choosing a particular reference frame, a particular way of slicing space-time. In a different reference frame, that galaxy might be a different distance away right now, because right now means something different. Distance across the universe is not a fact. It's a convention, a choice. We pick a reference frame, typically moving coordinates, where the cosmic microwave background looks the same in every direction, and we measure distances in that frame. But that's our choice. Another civilization on the other side of the universe, moving differently through space-time, would measure different distances. Who's right? Both of them. Neither of them. The question doesn't have a unique answer because distance across cosmological scales is frame-dependent. This is not a technicality. This is telling us something deep about the nature of space. Space doesn't have a fixed size because size is not an intrinsic property of the universe. It's a property of the measurement of the observer of the coordinate system you choose. The universe doesn't come with a built-in ruler. Now let me push even further. Let me talk about the metric because this is the mathematical object that encodes everything about distances and sizes in general relativity. In general relativity, the geometry of space-time is described by something called the metric tensor. The metric tells you how to measure distances and time intervals between nearby events. It's the mathematical DNA of space-time. And here's what's crucial. The metric changes. It's not fixed. It's dynamical. It evolves according to Einstein's field equations. Responding to the distribution of matter and energy, the expanding universe means the spatial part of the metric is changing with time. Distances between comoving points are increasing not because the points are moving through space, but because the metric, the very definition of distance, is changing. Let me give you an analogy. Imagine you're an ant on a balloon. The balloon is being inflated. You and another ant are sitting still on the surface. Neither of you is walking. But the distance between you is growing because the surface itself is stretching. Now, does the balloon have a size? Well, you can measure its circumference at any given moment. But the number you get depends on when you measure it. A second later, the number is bigger. A second before, it was smaller. What's the real size? There isn't one. The size is a function of time, not a fixed property. And the universe is like this, but much stranger, because unlike the balloon, the universe might not have an outside. The balloon is embedded in three-dimensional space. You can look at it from outside and say, there it is. It's this big. But the universe, as far as we know, is not embedded in anything. There is no outside. There is no vantage point from which you could look at the whole thing and measure it. The universe is all there is. Asking how big it is like asking how big is everything. The question doesn't have a well-defined answer because there's no reference frame outside the universe from which to make the measurement. This is a point that I think most people never fully absorb. Size is a comparison. Something is big compared to something else. A mountain is big compared to a person. A galaxy is big compared to a star. But the universe as a whole, what do you compare it to? There's nothing else. There's no external standard. The universe is the standard. And a standard cannot measure itself. Now let me tell you about something that makes this problem even more radical, inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. This is the theory of cosmic inflation, proposed by Alan Guth in 1981, and it solves several deep problems in cosmology. But it also makes the question of the universe's size essentially meaningless. During inflation, the universe expanded by at least a factor of 10 to the 26th, maybe much more. Some models of inflation predict expansion factors of 10 to the 10 to the 100, a number so large it has no physical meaning that your brain can grasp. After inflation, the universe was already enormous beyond comprehension. And it kept expanding for 13.8 billion years. at varying rates, and it's accelerating now. So the actual universe, beyond what we can see, could be so unimaginably large that the observable universe, all 93 billion light years of it, is less than a grain of sand in comparison. Less than an atom, less than a Planck length compared to the whole. And if inflation is eternal, which many of the best theoretical models predict, then the universe isn't just very large, it's infinite. Actually infinite. Not approximately infinite. Not really, really big. Infinite. Now, an infinite universe doesn't have a size, obviously. If it extends forever in every direction, the concept of size simply doesn't apply. But even a finite universe might not have a well-defined size. If the universe has a positive curvature, like the surface of a sphere, but in 3 spatial dimensions, then it's finite but has no boundary, no edge. You could travel in a straight line and eventually come back to where you started, like circumnavigating the Earth. Such a universe has a circumference, sure, but that circumference is changing every moment as the universe expands. And depending on when you measure it, you get a different number. And depending on what reference frame you use, you get a different number. And from the inside, you can never see the whole thing at once because of the cosmic horizon. So even in this case, asking for the size gives you something that's ambiguous, frame-dependent, time-dependent, and practically unmeasurable. Let me bring this back to something more visceral. Think about the room you're in right now. You feel like it has a definite size. The walls are a certain distance apart. Your body occupies a certain volume. Everything feels solid, fixed, measurable. But even at this scale, size is stranger than you think. What determines the size of your body? The distance between your atoms. And what determines that distance? Electromagnetic forces, the repulsion between electron clouds in adjacent atoms. If the electromagnetic force were slightly different, your atoms would be a different size. You would be a different size. The room would be a different size. Size at the atomic scale is determined by the constants of nature. Planck's constant, the electron charge, the mass of the electron. Change any of those, and the size of everything changes. And here's the deep question. Why do the constants of nature have the values they do? We don't know. In the string theory landscape, which I've spent a good chunk of my career working on, there might be 10 to the 500 different possible sets of constants. In most of those, atoms don't even exist. In the ones where atoms do exist, they might be vastly different sizes. The size of everything in our universe, from atoms to stars to the observable universe itself, is an accident of which vacuum state we ended up in. The size of things is not fundamental. It's emergent, it's contingent. It depends on the particular physics of our particular universe. In another universe, with different constants, size itself might mean something completely different, or it might not exist at all as a meaningful concept. Let me push into one more territory that I think is crucial, the holographic principle. This is something I've worked on personally, and it has profound implications for the nature of space and size. The holographic principle, which emerged from the study of black holes and was developed by Gerard Hooft and later by me, states that the information contained in a volume of space can be fully described by information on the boundary of that volume. Think about what that means. The 3-dimensional interior of a region of space is completely encoded in the 2-dimensional boundary. It's as if the 3-dimensional world is a hologram, a projection from a lower dimensional surface. In the most well-studied example, the ADESC CFT correspondence discovered by Juan Maldacena in 1997, a certain kind of higher dimensional spacetime containing gravity is exactly equivalent to a lower dimensional quantum field theory without gravity on its boundary. The bulk and the boundary describe exactly the same physics, just in different languages. Now, if the 3-dimensional world is equivalent to a 2-dimensional description, what does that say about the size of the 3-dimensional world? In the boundary description, the radial direction, the direction that gives you the 3rd dimension, is emergent. It comes from the quantum properties of the boundary theory. Distance into the bulk isn't fundamental. It's constructed from entanglement patterns in the boundary quantum field theory. The size of the extra dimension literally depends on the quantum state of the boundary. Change the state, change the geometry, change the entanglement, change the distances. Space and its size are not fundamental. They emerge from more primitive quantum information. This is one of the most radical ideas in modern theoretical physics. And it's not just speculation. The mathematical evidence for the ADESC CFT correspondence is overwhelming. Thousands of calculations have confirmed it to extraordinary precision. If this picture is right, and I believe it is, then asking how big is the universe is like asking how big is a hologram. The answer depends on whether you're talking about the holographic film or the projected image. And the two can have completely different dimensionalities and sizes. The projected image, the space-time we experience, has size, but that size is derived emergent, not fundamental. The fundamental description might have a completely different notion of extent or no notion of extent at all. This connects to another deep idea that has been gaining traction in theoretical physics. The idea that space itself might be an emergent phenomenon, that at the deepest level, there is no space, no distance, no size, just abstract quantum information, qubits in some vast quantum system, and spacetime emerges from the entanglement structure of those qubits the way temperature emerges from the motion of molecules. If this is true, and I think there are very good reasons to take it seriously, then the universe doesn't have a size any more than a dream has a size. The space-time we experience is real in the sense that our experience of it is genuine, but it's not fundamental. It's a collective phenomenon emerging from something deeper, something that doesn't have spatial extent at all. Let me tell you what disturbs me most about this. We have built our entire understanding of reality around the idea that things have sizes. That space is out there, extended, measurable, concrete. Our physics, our engineering, our everyday experience, all of it assumes that distance is real. And it is real in the same way that temperature is real. Temperature is a real property of a system. You can measure it. It affects what happens. But temperature isn't fundamental. It's a statistical property of the collective motion of particles. You can't point to a single atom and say this atom has a temperature. Temperature only makes sense at the macroscopic level. Size might be the same way, real at the macroscopic level. Meaningful for everyday physics and engineering, but not fundamental, not part of the deepest description of reality. Just an emergent property of whatever the true quantum gravitational degrees of freedom turn out to be. And if size isn't fundamental, then neither is the size of the universe. The question, how big is the universe, might be like asking what's the temperature of a single electron. It might be a category error. A question that sounds meaningful, but isn't, because it's applying a macroscopic concept to the wrong level of description. Now, I know this is hard to swallow. It was hard for me to swallow, and I've been thinking about it for decades. We're so used to space being real and concrete and out there that the idea of it being emergent, derivative, not fundamental, feels like the rug is being pulled out from under us. But this is what physics does. It pulls rugs. It pulled the rug when Copernicus said we're not at the center. It pulled the rug when Darwin said we're not specially created. It pulled the rug when Einstein said time is relative. And now it might be pulling the rug again, saying space itself is not what you think it is. Let me talk about one more thing before I wrap this up. Dark energy. Because dark energy makes the question of the universe's size not just philosophically problematic, but physically bizarre. Dark energy is the mysterious force driving the accelerating expansion of the universe. We don't know what it is. Not really. The simplest explanation is Einstein's cosmological constant, a constant energy density permeating all of space. And here's the weird part. If the cosmological constant is truly constant, if the energy density of the vacuum doesn't change as space expands, then as the universe expands and creates more space, it also creates more energy. More space means more dark energy. More dark energy means faster expansion. Faster expansion means more space. It's a feedback loop, an exponential one. And it means the universe will continue expanding forever at an accelerating rate, with the rate of expansion approaching a constant, the de Sitter rate. In the far future, trillions of years from now, the observable universe will contain only our local group of galaxies. Everything else will have been swept beyond the horizon. The sky will be dark, the universe will be cold, and it will be expanding faster and faster, creating more and more space that we can never see, never access, never interact with. In this scenario, the universe literally has no final size. It grows without bound. It was already probably enormous beyond comprehension after inflation. It has been expanding for 13.8 billion years since then, and it will continue expanding forever. The size of the universe, if you insist on assigning one, is a number that increases without limit. It was big yesterday. It's bigger today. It will be bigger tomorrow. And there will never be a day when the expansion stops, and you can say now it's this big. The number never settles. And here's something even more unsettling. In eternal inflation, which is the best framework we have, for the very early universe, our entire observable universe, all 93 billion light years of it, is just one tiny bubble in an infinite, eternally inflating sea. Other bubbles are forming all the time, each one potentially an entire universe with its own laws of physics, its own constants of nature, its own particles and forces. The multiverse, I've written about this. I've defended this picture. And in this picture, asking for the size of the universe is like asking for the size of the ocean while standing in one raindrop. You can measure the raindrop. That's your observable universe. But the ocean, the totality, it's beyond your reach, beyond your measurement, beyond your comprehension. And it might be literally infinite. Multiple infinities, in fact, no. Since eternal inflation generates an infinite number of pocket universes, each potentially infinite in its own spatial extent. What does size even mean in such a context? I don't think it means anything. And I don't think that's a failure of our understanding. I think it's a feature of reality. Reality at its deepest level might not have a size. Space might not have a fixed extent. Distance might not be fundamental. And the question, how big is the universe, which seems so simple and so natural, might have no answer. Not because we're ignorant, not because our instruments aren't good enough, but because the question itself doesn't make sense at the level of fundamental physics. Let me be clear about what I'm saying and what I'm not saying. I'm not saying the universe doesn't exist. It obviously does. I'm not saying distances aren't real in everyday life. They obviously are. I'm not saying we should stop doing cosmology or measuring things. We absolutely should. What I'm saying is that the concept of size, the concept of spatial extent, it might be something that only makes sense at our level of description, the macroscopic level, the level of everyday physics. At the deepest level, the level of quantum gravity, of holography, of the fundamental degrees of freedom, whatever they turn out to be, size might not be part of the vocabulary. The universe might not have a size for the same reason that the number 7 doesn't have a color. It's not the kind of thing that has that property. And I find that both terrifying and beautiful. Terrifying because it undermines our most basic intuitions about reality. Beautiful because it hints at something deeper, something more profound, something we haven't fully understood yet. After 50 years of thinking about these questions, I can tell you that the universe keeps surprising me. Every time I think I've reached the bottom, there's another layer underneath. Every time I think I understand what space is, it turns out to be something else entirely. The universe has no size, not because it's too big to measure, not because our telescopes aren't powerful enough, but because size itself, at the most fundamental level, might not be real. And that, I think, is far more interesting than any number anyone could ever give you. Think about that the next time someone tells you the universe is 93 billion light years across. They're not wrong exactly, but they're telling you about the shadow on the cave wall, not the thing casting it. The real universe, whatever it is, doesn't fit inside a number. No, it doesn't fit inside a measurement. It doesn't fit inside the concept of size at all. And we're only beginning to understand why. Thank you for listening. Go outside tonight. Look up at the stars. And remember, and the space between you and those stars might not be what you think it is. It might not be anything at all. And that's the most wonderful, most unsettling, most profound thing I've learned in 50 years of physics. The universe is stranger than we imagined. And it doesn't come with a tape measure.